This next video lesson is going to talk about integrated or differential rate law graphs. And as you probably would suspect if you have any sort of calculus background, that this particular concept can be taught using calculus. But again, as I mentioned in video lesson 1, my background in calculus isn't that strong. And so I'm not really going to talk about integrated rate laws in terms of calculus concepts, but just simply based on what you need to know to get an A on the test or what you'd most likely see on the AP test. The first thing you need to know about integrated rate law graphs is that they're named or identified by an overall reaction order. Now what an overall reaction order is just the sum of the individual orders of the reactants themselves. And so if you have two reactants, both that are first order, they add up to be a second order overall reaction. The second thing you need to know about these rate law graphs is that they're all concentration versus time graphs. So I'm going to show you graphs for a zero order, a first order, and a second order, and they're all going to be a graph that represents changing concentration versus time. And the last thing that I want to talk about is that each graph, the zero, the first, and the second order, can be manipulated mathematically to represent a straight line. Straight lines are useful to us because when you set up a graph in a straight line, you can generate a line of best fit in the form of y equals mx plus b, and then you can do some other calculations involving that line. Now we're going to apply that straight line formula to the three different graphs as it pertains to each case. Let's begin with the zero order reaction. Now the first thing you want to know about the zero order reaction is it's the rarest form of a reaction that you'll ever come across in real life. Now we'll talk about it in terms of academics, and you should understand what it is and how it's used, but I'll let you know that in reality, a zero order reaction very rarely happens. Now the rate law for a zero order reaction would look like this, where the reaction may be actually like a diatomic element and its gas state kind of just splits up into two individual atoms, both of which in their gas state. So think of a decomposition of a diatomic molecule. Now oftentimes this zero order reaction is one step in the process of a many-step process in order to maybe produce a particular product. And so the zero order reaction itself stands alone by itself very rarely, but is often used as in a sequence of steps. So here's a sketch of a graph. We've got molarity on the vertical axis and time along the horizontal. I'm going to pick a point on the vertical axis and we're going to label that the concentration of A at time 0. Basically, when you have 0 seconds, the initial concentration of your reactant. We talked about this on a previous video lesson, but anything that's zero order means that when the concentration changes, the rate is unaffected. And so what you would observe in a zero order reaction is once the reaction begins to start, the concentration just decreases in a very linear fashion over time. In other words, the rate of this reaction is directly related to the K constant, because anything to the 0 power is 1, so K to the 1, the concentration is unaffected. So K times 1 equals the rate, or just K equals the rate. And if rate is defined as molarity per second, then K is equal to molarity per second. So at any point along this graph, if you take the molarity divided by the seconds, you will get K, and that number is the same no matter which point you pick on this line, assuming the line is drawn straight, which is what you're going to assume for my little sketch. So what I'm telling you is that the slope of the line is equal to the K constant, which is equal to the rate in this case. Now at any given point along this line, we can choose a spot here, and we'll call that the concentration of A at times t. So some arbitrary time down the path of this chemical reaction occurring. So if my y-intercept is defined as the concentration of A at time 0, and the slope of my line is proportional to K, and since K the slope of the line is negative, I'll call it negative K. The variable along the x-axis is time, and if I add those together, I get what is equal to the concentration of A at time t. Now if you look very closely at what I just drew, I basically just drew you the formula for a line in the form of y equals mx plus b. But instead of y and x and m, I use K and the concentration initial and the concentration at times t. So what you can do with this formula of this line is if you know two of these three variables, you can solve for the missing variable. So if I give you an initial concentration and a final concentration and say, I can ask how long it took for this reaction to occur, assuming you know K. Or if you know K and you know initial concentration, I can say, what is the concentration after 30 seconds? Now all this information is kind of overwhelming, and many of you might be wondering, how am I supposed to remember all this? Well, what you really need to know is how to apply this formula. And this formula will be given to you on your formula sheet on the back side of your periodic table. Also, what you'll need to know is if you're given a graph and you're given axis of molarity in seconds and the line looks like this, then you should be able to identify the order of the reaction from what the axes and the shape of the graph look like. Next, we're going to talk about a first order reaction. Now, as rare as zero order reactions are, first order reactions are around all the time. A reaction that is first order might have just one reactant, or it could have two reactants. So a rate law for a first order reaction, as you can see, would just be a to the first power, or it could be a to the first power at b to the 0, where it would have two reactants, but one reaction does not affect the speed overall of the reaction. What you see over here is a graph, and I've actually graphed the slope of a zero order relationship, which we just talked about on the last slide. It's a straight line in a concentration versus time graph where the slope of the line is equal to negative k times t. Now, I just juxtapose the first order curve on the same graph to show you what a first order reaction looks like when you graph it in concentration versus time. You get concentration affecting the speed of the graph. You can see that as you go and progress over time that the sloped line, the tangent line to this slope becomes less and less steep. And the slope line, which is tangent to the graph, represents the rate, as we talked about in a previous video lesson. Now, if I wanted to, I could draw in even the second order graph and on top of the first and zero order, and what you would see is a immediate decline and immediate level off. And so the second order would basically reach a flat line much sooner than the first order because you're reacting everything very quickly. And so once you get out past a certain number of seconds, as time progresses on, the slope of the line remains unchanged and eventually turns flat. And when you have a flat line, even with no slope, you have no rate. But we're getting ahead of ourselves a little bit for second order graphs. So let's talk about first order reactions. Now, if I took the first order graph, the first order curve in red here, I could figure out the slope of the line by taking the derivative. But I don't really want to do that. Again, I'm going to shy away from calculus concepts and instead just kind of talk about algebra concepts and what you need to know to understand this on a surface level. So what I can do is manipulate the first order graph to be linear by simply taking the natural log of a. So if I redraw the graph and instead of identifying the vertical axis as just concentration of a, I call it the natural log of a. And I start at a at time 0. Then I go along as time progresses, and because it's natural log of a at time 0, over time it represents a linear relationship. And like I did before, at some point on the line I can pick a concentration after a certain amount of time. And because it's now a linear relationship, I can apply a y equals mx plus b formula to this to help me be more predictive in my ability to do first order reactions. Essentially, if I know two concentrations, I can figure out the time it took to get to that point, or if I have the initial concentration and a time, I can figure out what the concentration is after that certain amount of time. But I need to generate a line, and the formula for that line should be in y equals mx plus b. But unlike the last graph, which had a and a at time 0 and a at time t in the form of just concentration, I now have the natural log. So again, my y-intercept, which is the point of the line where it crosses the vertical axis, is a at time 0, but I'm going to call that natural log of a at time 0. I'm still going to add that to negative k times t because, again, k is essentially my slope, and t is my x. K is m, t is x, plus b, mx plus b. And that is all set equal to a at concentration of a at time t. In fact, it's concentration of the natural log of a at time t. Your formula sheet will have this on the back, that formula sheet, the one on the back side of your periodic table, but it might not look exactly like that because we draw ours in the form of y equals mx plus b, but the back of your formula sheet has it in standard formula or standard form. So if I rearrange this so that I isolate the kt on one side, I subtract natural log of a at time 0 on each side, and I get negative kt is equal to the natural log of a at times t minus natural log of a at time 0. And this is what the back of your periodic table shows. It's simply y equals mx plus b rearranged so all the a terms are on one side and the k times t term is on the other, which is, again, just simply the y equals mx plus b form of the line written in standard form. In summary, as it was with the last one, all you need to know is how to apply the mathematical relationship if you're given data, or to be able to identify the order of the reaction given the given the linear version of the graph. So, for example, I say, what would the vertical axis read on the linear version of a first order integrated rate law graph? And you would say natural log of a. If I said, what's the vertical axis of the straight line graph of, say, a 0 order reaction, you'd say just concentration of a. All right, let's finish off with second order reactions. And so a second order reaction would present itself in a situation where you have like first order with both respect to A and B if you had two reactants, or one reactant that has second order all by itself. Remember, the overall reaction order is dependent on the sum of the reactants' orders. So 1 plus 1 is 2, or just single reactant with the second order. Now, this first graph is a copy of the one from a couple slides ago. You basically have the concentration of A versus time. And as you can see, I put the first, second, and third, 0, first, and second order graphs all on the same graph. You can see how the first 0 order is linear, the first order has a steep drop but flattens out, and the second order drops very slightly and flattens out very quickly. Now if I take a second order reaction and plot it in natural log versus concentration, you can see that it still has a decay sort of curve to it. So that's not very useful to us. Ultimately, we want to find a graph. We want to manipulate a graph, a second order graph, that gives us a nice straight line. And so this is just concentration versus time, not useful. This is natural log versus time, and if this was first order, natural log versus time would be straight, but it's not straight, it's curved. So that means it's not a first order reaction. Finally, we have this third graph down here. You can see the axis is not natural log or even concentration, but 1 over the concentration. 1 over the concentration versus time gives us this nice positive linear relationship. And linear relationships are good for us because we can apply a line linear function to it. Now again, the y-intercept is the point at which the line begins at the y-axis. So this is time 0. What's the concentration? And if you take 1 over the concentration, it begins to plot a linear relationship. And after 300 seconds, say, we plot a point that is the concentration of A at times t. So of all three of these graphs, all representing second order reactions, but all having slightly different vertical axes, the one that's most useful to us is this one. The first one just as concentration versus time, not useful. Natural log versus time, not useful. 1 over concentration, very useful. So if I plot the line once again, and I write out the formula for that line, the y-intercept will be 1 over A of the concentration A at times 0, because that's the y-intercept. Now because it's a positive slope, I go plus k times t and set that equal to the 1 over the concentration of A at times t. And again, I mean, it's pretty redundant, but I'm going to say it again. This is in the form of y equals mx plus b, or slope-intercept linear graph. Now on your formula sheet, they'll rearrange this so that all the a terms are on one side. And so on the back of your formula sheet and on the sheet that you'll get with the AP test, it'll have a at times t minus a at times 0 equals positive kt. That's just simply rearranging the y equals mx plus b formula so all the a terms are on the same side. Subtract 1 over a to the at times 0 on each side, and you'll get this new rearranged formula. So I showed you different integrated rate law graphs of 0, first, and second order. And again, it's worth summarizing that the two things that you need to know from these graphs are, number one, be able to identify the graphs based on which give us a straight line and what do the axes look like. And the last thing that I'd expect you to do is how to apply the mathematical formula to solve a problem. So here are two examples of problems that you'd expect to see as it pertains to integrated or differential rate laws. Let's take a first look at this first one. Okay, so you've got a couple of graphs here. You've got graph A and graph B. It says, what can you conclude from the fact that the plot of ln of p versus t is linear? And so what you have here is, instead of concentration on the vertical axis, you have pressure. And as we talked about in the gas law chapter, that pressure and moles are directly relational. There's a direct relationship between them. So if you know pressure, you know moles, and if you know moles, you know pressure. That relationship is Pivnert. So pressure and molarity, really, it means the same thing. So in a pressure versus time graph, you can see that it's not linear. It goes down, down, down. It flattens off eventually. Now, in my mind, this could be either first or second. So I know it's not 0 because pressure versus time is in a nonlinear. If it were linear right off the bat, it would be a 0 order. So I've narrowed it down to first or second. So now I look to this problem, or this graph. It's the same set of data graphed in natural log of pressure versus time. And now it's in a straight line. So in my mind, I go, oh, well, that's first order, because natural log versus time in a straight line is first order. So that's what I mean when I say be able to identify the different orders based on the straight line graphs. Now, and if this was the case, if you had natural log of the pressure versus time and it still wasn't linear, then you can safely assume that by process of elimination, then the reaction must be second order. But this right here, this relationship here, means it's in a straight line, must be first order. Now the second one is going to take a little bit of calculation, and we're going to give ourselves a little bit of room to be able to answer this. So let's first start with what's given to us in the problem. Okay, we've got the decomposition of sulfuryl chloride. Don't really need to know what that is, but what I do need to know is that it's a first order process. All right, so first order, take note of that. That's going to be important when deciding which formula to use. Second of all, we've got a rate constant at 660 is this. Also, not all that important to us necessarily right now. It's just a number. We're going to apply that. So I know that this is a first order problem because it's said in the problem. So it's a first order, and we're going to answer A. If we begin with the initial concentration, or the initial pressure in this case is 450 torr, what is the pressure of this substance after 60 seconds? Now, first order means that I'm looking at an ln of p at time 0 minus kt is equal to the natural log of p at time t. Because first order rate log graphs, when you graph them in a linear form, have natural log in their formula. So I'm going to use this form of the line formula. Now as you can see, I simply just substituted in p at time 0 and p at time t in for a at time 0 and a at time t, but the same math would apply. So at this point, all this really is plug in the numbers from the problem and solve for the missing variable. In this case, the missing variable is what is the pressure after a certain amount of time has passed, or pressure at time t. So I took the 450 as the initial pressure, put that here. Oh, forgot that I have to take natural log of that. So that's a key thing. People often forget to do that. I have to take the natural log of the initial pressure and subtract it from 4.5 times 10 to the negative second times 60, and set that equal to the natural log of pressure at time t, or just call that natural log of x if you want. So punch this into my calculator and see what I get. So the first thing I did was take the natural log of 450, and I got this number. Now, I rounded that off, but I'm going to keep that whole number in my calculator because I'm just going to want to round once at the end. So I got this number, and then I took 4.5 times 10 to the negative second and multiplied by 60, and I got that number. So now I'm going to do the math and solve for natural log of pressure at time t. So after I quickly subtract 6.109 minus 2.7, I get 3.409 equal to natural log of pressure at time t. I just need to take the inverse of the natural log on each side to isolate p at times t. And my answer is 30, or 30 torr. So doing all this, plugging in the numbers, and just solving for p at pressure times t, I should get 30 torr. And I want to use two significant figures because my initial pressure was two significant figures. And this technically is one significant figure, but one sig fig problems are really bad. So I'm just going to add a decimal behind that 0 to make sure it has two significant figures. So that answers part A. Now let's tackle part B, shall we? Part B asks, at what time will the pressure decline to 1/10 of its initial value? So initially it's going to start at 450 torr. The K constant still remains 4.5 times 10 to the negative second. But this time we're solving for t. It says what is the time when the pressure is declined to 1/10 its initial value. So I'm going to put t as in my missing variable. Now on the other side of the equal sign, I'm going to put natural log, and what's 1/10 of 450? Well, it's 45. So now I have everything except t, and I solve for t. So once again, I take natural log of 450, and I get 6.109, subtract 4.5 times 10 to the negative 7th times t, and this side, natural log of 45 is. What I want to do now is isolate t so it's by itself. So I'm going to subtract 6.109 from each side, and I get negative 2.303. That's still equal to negative 4.5 times 10 to the negative second times t, and then I simply just divide by that number on each side to isolate t. And when I do that, t is equal to 51.1 seconds. And since I really want that in two significant figures, it's just 51 seconds. So that's my final answer. Well, that takes care of this rather long but very important video lesson. I hope you found it informational. Please let me know if you have any questions. Thanks for listening.